If the perspective is off, the angles will vary and be inaccurate. It also means objects will appear a different size to what they actually are. At college, we are lacking lots of the needed equipment to complete a thorough and detailed experiment. When our athlete completes the practical, we can capture some shots of the hall, people running and jumping, allowing the process of data collection. We can measure the times of a 20-meter sprint and the heights of a vertical jump. At a novice level, the type of equipment needed for serious data collection is just too expensive. Therefore, we can only use what we have access to. For us to conduct the vertical jump test, we had limited resources, meaning that we didn't have access to a professional force plate. We used a jump mat, however, instead. The subject wears a waist belt attached to a measuring tape that is grounded to the mat. We set the tape to 0, and then they jump as high as they can. The tape measure shows how the height of the jumps. This was then repeated 3 times to find the best score. Disadvantages of this are that the height measured will be inaccurate if you do not jump straight up and down. This system can also limit the athlete's movement. Further errors may occur due to the moment of inertia of the tape, and if the tape is loose to start with. Advantages, though, are that this device is inexpensive, portable, and easy to use. Testing can be conducted on your own. You can get a true vertical height displacement of the torso, and it is not reliant on the subject timing their jump to touch something at the peak of the jump. The apparatus can be used indoors and outdoors. The 20-meter sprint test involves running a single maximum sprint over 20 meters with the time recorded. The athletes completed a warm-up, including some practice starts and accelerations. They then start from a stationary position with one foot in front of the other. The front foot must be on or behind the starting line. The starting position should be held for 2 seconds prior to starting, and no rocking movements are allowed. The tester then timed the athlete for the whole 20 seconds, recording the time for every 5 meters covered. This means the tester needed to stand around the 10-meter mark so that they could see the whole area. When comparing the vertical jumps, we can see the difference between my performer, the group average, and the NBA elite athletes, as well as a better player. My performer and the better player had the same score of 72 centimeters. Compared to the group average, this was a difference of 24 centimeters. That's quite a significant amount for a straight vertical jump, showing that they were quite experienced. An NBA athlete has a jump of 97.8 centimeters. This huge height reach will be due to the power in their legs built up over time in order for them to jump with the ball to the net and score. Having this good vertical jump is very beneficial to elite athletes and helps them guarantee more accurate shots. We can also use data to compare the peak power in athletes' vertical jump. Sayers' formula, Sayers et al. 1999, estimates peak anaerobic power from the vertical jump. This can be worked out by 60.7 multiplied by the jump height plus 45.3 multiplied by the body mass minus 2055. My performer had a body mass of 73 kilograms and a jump height of 72 centimeters. This left us with a peak power of 5,622.3 watts. In comparison, elite NBA player Dorian Finney-Smith had a mass of 100 kilograms and a height of 97 centimeters, meaning he had a peak power of 8,362.9 watts. As well as his jump being higher, his mass was a lot more, resulting in this higher peak power. Heavier players tend to generate more power. My athlete ran the whole 20-meter sprint in a total of 2.6 seconds, which is a very quick pace for a non-elite player. As you can see from the distance chart, the increase of time and distance is very linear. From this data, we can work out speed by calculating the distance divided by the time. For each 5 meters, the change in time from one post to the next can be used to calculate this speed. From there, we can analyse whether a player has sped up or slowed down for every 5 meters that they've run. My athlete sped up consistently between each 5 meters, going from a speed of 6.49 to a speed of 10 meters per second. This slight increase can be seen by the gradient in the distance graph. For this data, our velocity is calculated as the same as the speed, as our athlete was only travelling in one direction. Therefore, the speed and velocity is demonstrated on this velocity graph. There is an immediate spike in the first second as the athlete goes from being still to sprinting. The speed then continues to increase but levels out slightly for a slower increase. The athlete would continue to speed up until they reached their maximum and began to fatigue. If we were to calculate the results from a 100-metre sprint, we would likely see this maximum reached around 20 to 25 seconds, where our athlete would then reach a plateau speed and potentially slow down before the end of their race. Acceleration can then be calculated by dividing the change in velocity by the change in time. Obviously, the acceleration increases dramatically as the player goes from still to sprint. This value then decreases before slightly increasing again. This could be due to the final push across the 20-metre line. When viewing the comparisons of the sprint times, we can see what speeds my player, the group average, and an NBA elite player were running. Compared to the group average, my player was very fast actually, being the quickest of the whole group. The group average was 3.7 seconds, but my player ran for 2.6 seconds. This is over a whole second faster. This might suggest that they play basketball regularly or some type of sport involving sprinting. The NBA elite performer's three-quarters sprint was 2.42 seconds, not much faster than my performer. Many disadvantages and advantages that come with the numerical model. Some advantages are that this type of analysis is most effective for elite performers. This is because they know how to complete the skill already. We can analyse it and compare it to other elite performers using graphs and data collection. The equipment and technology is also effective within analysis. This means that our results aren't based off of judgment but numbers. This data isn't difficult to collect and can be gained using simple or complex methods, depending on who's recording them and how important they are and what equipment they're provided with. This type of data is quantitative and it can be useful in goal setting. For example, if a basketball player was shooting 5 successful layups in a game, but worked on improving their layup technique, then next time they could aim for 7 successful layups. Data is easy to read this way and can easily be achieved or unachieved. There are also many disadvantages that come with a numerical model, this being that the advanced equipment can be difficult to use and is expensive and hard to gain access to. Often the only way to access this specialised equipment is to have access to it through somewhere like a university or a top performing team. The equipment has to be used by people who are experienced and not just by anybody. We experienced this ourselves as we didn't have access to a force plate for the vertical jump or laser gates for the 20-metre sprint. There also needs to be an academic understanding of the equipment and the data collecting, as well as being able to put all of this information onto a graph. The numerical model is not as effective for beginners or low-level performers. This is because it does not take into account the technique used. Therefore, if beginners have a poor technique, it doesn't matter how high they jump if they're doing it wrong. The best way to use this would be on someone who is completing the tasks properly and effectively. Thank you.